Well, we will now turn to the topic of rotation. So let's first just consider an object turning about some kind of axis. I've labeled the axis here of this object just with a little x. And let's imagine the object is rotating, and I want to look at 2 points, and I want to compare 2 points, point A and point B, where A is a little closer to the center or closer to the axis, and B is a little further away from the axis. So let's say this object takes some time t to rotate, and this time t has a special name, which is called the period, and it's measured in seconds, that it takes to rotate. I don't know, 1 second, 2 seconds. If it's going really fast, maybe a small fraction of a second. Note then that points A and B, as this thing rotates, both traverse circles. And we could find the velocity of these points, right? The velocity of point A, well, assuming it's rotating at a nice constant rate, which is where we're going to start. Point A covers a certain distance, covers the circumference of a circle in some time period t. So that's going to be 2 pi times the radius at point A over t. So that's, well, it goes through the whole circle in time period t. And point B then would be 2 pi RB over t. And so one thing jumps out immediately, which is that even though this whole object is rotating all together, points further away from the axis are actually moving faster, have a greater linear speed, and this is again in terms of meters per second, have a greater linear speed than points closer in. This makes our lives sometimes a little difficult with rotation, that 2 points on the same object can be moving at very different speeds. So what we always like to find in physics is something that is the same. We have this idea that an object is rotating as one object. So what is the same? So we're actually going to shift our focus a little bit in rotational motion. And we're going to say, well, what if I kind of take this dotted line and I look at the angle that point A and B are at relative to that dotted line. And hopefully you can see that as this object turns, the angle of A and the angle of B are always the same. And so if we track that angle theta, we actually can define a new quantity that we're going to talk a whole lot about, which is called omega, this fancy W. And we're going to define omega here as the derivative, as the rate of change of that angle. Notice that this has units of radians per second, angle over time. It has units of radians per second, and we have a special name for this. We call this the angular velocity. And what's nice about this is that although A and B have very different linear velocities, they have exactly the same angular velocity. And that's actually a really important point, that every point on an object that's rotating has the same angular velocity. So it becomes a very useful tool to talk about the motion of an object. So omega, this angular velocity, has some similarities to our normal velocity. It's still in units of something per second, although now it's radians rather than meters. We actually can convert it back to linear velocity. We can actually convert it back to linear velocity using what's going to turn out to be an extremely important equation. So I'm actually going to list our important equations over here. Omega is the rate of change of this. Note also that that means the average angular velocity is just delta theta over delta t. We do that kind of thing a lot. If you want to go back to linear velocity, though, you could just multiply by r. V equals r omega. So if I wanted to find the velocity of A, I would just multiply by the radius of A and so forth, where the radius is the distance from the axis. So this is a really important equation. V equals r omega. This is how you get back and forth between rotation and kind of those meters per second, what we call the linear speed. It's also worth noting that omega is a vector. It is a vector. And one of the funny things about omega is that we're used to vectors being pretty descriptive, right? If an object has a velocity vector that way, well, it's moving that way. What's kind of funny about rotational motion, here's a little disk. Here's its axis, and let's say it's rotating this way. In order to find the direction of the vector omega, what I actually am going to do is I'm going to take my right hand here, and hopefully in the mirror image this still looks like my right hand, and I'm going to curl my fingers in the direction of motion, in the direction of rotation, at which point my thumb, you'll notice, is forced to point up along the axis. And so in fact, the omega, the angular velocity vector, points directly upward along the axis. So the direction of omega, is along the axis of rotation, and it's whether it's going up or down, or which way it's going, is as per what we call the right hand rule. So you're going to use your right hand, curl your fingers with the direction of motion, and point your thumb up. That does mean, of course, that if this disk is rotating the other way, if it is rotating clockwise, that in order to do that, I have to flip my right hand upside down. And so here my omega vector is downwards. So counterclockwise is usually the positive, is the upward direction here. We can also notice, right, if we've got some angular velocity, right, we can actually turn this into a kinematics equation. We can kind of think about it in terms of change in angle over change in time. And we can just go ahead and rearrange this. That change in theta is going to be omega delta t. Or, if you want to write this a little differently, theta final equals theta initial plus omega delta t. And if this looks an awful lot like a kinematics equation to you, you are not wrong. They are, in fact, very much alike. And one of the things we're going to find is that for every linear quantity, there is an equivalent quantity in rotational motion. So instead of velocity, we have angular velocity. Instead of position, we have angle. Well, what if angular velocity is changing? Well, we can introduce a new quantity, which is called alpha, which is the derivative of angular velocity, or the second derivative of angular position. And this alpha, you might imagine, is called angular acceleration. And it has units of radians per second squared. It's also a vector. Its direction is the same as omega. We find its direction in the same way as we find the direction of omega, so it also points along the axis. And one thing that we're actually going to find is a really, really, really helpful thing, which is that for every single linear equation, every single linear kinematics equation, there's a rotational equivalent. So, for instance, we've got our first kinematics equation, final velocity equals initial velocity plus a delta t. Well, in rotation, that's just omega final equals omega initial plus alpha delta t. It's the same equation, just with all of our linear velocities and accelerations replaced with rotational ones. Instead of our second kinematics equation, right, x final equals x initial plus v0 delta t plus 1/2 a delta t squared. We can instead of position, we're going to use angular position plus omega 0 delta t plus 1/2 alpha t squared. And we even have our third kinematics equation, which we can put into rotational quantities, right? So instead of v final squared equals v initial squared plus 2a delta x, we instead, and I'll write it down here in the interests of space, omega final squared is omega 0 squared plus 2 alpha delta theta. So we have a bunch of different equations here, and the important thing is all of the intuition you've built over this year so far for linear kinematics, you can apply directly to rotational kinematics. So if I give you a graph, for instance, of, you know, angular velocity versus time, the slope of this graph should be our angular acceleration. And the area under this graph, well, the area under a velocity graph, should tell us our angular displacement. And so the idea is we can use all of our old kinematics knowledge and just translate it over to rotation. So let's do a quick little example here at the bottom. So we're going to have a wheel that starts at rest. It starts at rest, and then it spins up to an angular velocity of 4 radians per second over 2 seconds. So it starts off and spins up. So the first question we want to ask is, what is the angular acceleration of this, assuming that it's constant? Well, how would we find normal acceleration? Normally, our average acceleration would be change in velocity over change in time. So here, if we want to find our average alpha, it should be change in omega over change in time. So in this case, it started at 0, went to 4 over 2 seconds. So that'll be 4 over 2, or 2 radians per second squared. And we could also ask ourselves, well, how far does the wheel move in that time? How far does it actually rotate? And we could use our second kinematics equation, right? That the final theta is going to be equal to, well, it starts out at no velocity at all. It starts out at rest, so 1/2 alpha delta t squared, in which case we're going to get 1/2 times 2 radians per second squared times 2 seconds squared. So that'll be 4 radians. How far is 4 radians? Well, remember 2 pi radians, so about 6 1/4 is a full turn. So in this case, it goes not quite a full turn before over those 2 seconds. It's gone, you know, a little over halfway around. So the important thing is, as you're looking at the problem set this week, is to remember rotational kinematics problems are actually exactly the same as linear kinematics problems. It's just you've got to change your variables. So instead of position, we have angular position. Instead of velocity, angular velocity. Acceleration, angular acceleration. And we're actually going to see that through line through the whole rest of this unit, that every linear quantity has a rotational quantity. So where we used to talk about force, we'll talk about torque, which is the rotational equivalent of force. Instead of momentum, for instance, we'll have angular momentum. And even the equations stay very, very similar. We're going to have an equivalent to Newton's second law, F equals ma, and it's going to involve torque. As a spoiler, it's torque equals I alpha. So just like forces cause linear acceleration, torques cause angular acceleration, and so on. So the thing about rotation as we launch into this unit is that it's a whole bunch of new symbols and a whole bunch of new concepts. But the more you can stay grounded in what you already know about linear motion, the happier you're going to be with rotational motion.